Hello, this video is going to go through an example of solving a polynomial inequality. When solving a polynomial inequality such as this one, there's two things that you want to make sure are done first before you really get into the steps of solving. So the first thing is you want to make sure that the inequality is rearranged so that one side of the inequality is 0. In this case, that's already done. If not, you can use opposite operations to make sure that all of the terms are on one side and zeros on the other side. The second thing you want to make sure of is that when you have one side equal to 0, you want to make sure that the other side is in fully factored form. So again, in this case, that's already done for us, but if it's not in fully factored form already, then you will need to factor somehow. So that could be using factor theorem or decomposition or common factors, but you want this in fully factored form. Okay. So when we look at polynomial inequalities, there's really two strategies that we tend to use to solve these. And that's either using a more algebraic approach or a more graphical approach. And so we're going to go through both here. Often for polynomials, the graphing method is seen as an easier method, but I'm going to go through the algebraic method as well, because when we solve rational inequalities or some more complex inequalities than just polynomial, the graphing method may not work out as nicely. So if we're using the graphing method, the first thing that we're going to do is take this polynomial that has now been fully factored, and we're going to give it a function name. So we're going to call this one f of x is equal to x plus 3 times x minus 2 times x plus 5. And if we're able to get a graph of what f of x looks like, then we should be able to use that graph to determine where is f of x less than or equal to 0. And that would solve the inequality. So here, if we find the zeros of f of x, we set f of x to 0 and then solve the resulting equation. So we have either x plus 3 is equal to 0. That gives us x equals negative 3. Or x minus 2 is equal to 0. That gives us x equals 2. Or x plus 5 is equal to 0. And that gives us x equals negative 5. So these are the three zeros of this cubic function. And we also know that since the leading coefficient of this cubic function is positive, we know what the end behavior would look like as well. So when we graph this function, we know that the x-intercepts, or the zeros, are at negative 3, positive 2, and negative 5. And so just drawing a very quick sketch of this function using the appropriate end behavior that we know about for cubic functions with a positive leading coefficient, we get something that looks like this. And we're not going to really spend a whole lot of time here trying to figure out what the y-intercept is or what the maximum and minimum points are, because all we're really concerned with here is where is this function f of x less than or equal to 0? Well, we know it's equal to 0 at those zeros that we just solved for. So it's equal to 0 at negative 5, negative 3, and at 2. So we want to make sure that those values are included in our solution set for this inequality. We also want to know when is the function less than 0. And here we see that the function is less than 0 for this part of the graph and for this part of the graph. So those are the x values that we want to include in our solution set. So here, our solution set would be x is any number from negative infinity up to negative 5. And because this inequality is less than or equal to 0, we want to also include that negative 5 value. And also from negative 3 to positive 2. And again, we want to include those values because the function is equal to 0 at those two values. So that's how we can get to a solution set for a polynomial inequality using a graphical method. Okay, Now, if we look at a more algebraic approach to solve the same inequality, the same first two steps would apply. So you still want to make sure that one side of your inequality is equal to 0 and that the other side is in fully factored form before you proceed. And then at that point, we still want to start by determining the zeros of the polynomial on that you factored. So we would start by determining the zeros of the function f of x. So I won't write out the entire process again, but we are going to start by defining a function f of x and determining the zeros. So here we've already solved for those. We know that the zeros are the x values of -3, +2, and -5. And so what we want to do is algebraically, we're going to test out some values in this function f of x to determine where the function equals 0 and where the function is greater than 0 and where the function is less than 0. And so we know that for this particular function and for any polynomial function, the characteristic on the graph of that function that determines whether the function is positive or negative would be the location of the zeros, right? If we look back to this graph here, the location of the zeros is where the function changes from being negative or less than 0 to positive or greater than 0, or vice versa, changes from positive to negative. So it's those zeros that kind of break up where those positive and negative intervals are happening. So if we can determine those somehow, then we will have our solution set. So the way we organize this is as follows. Along the left-hand side of a table, I'm going to list the factors of this polynomial function f of x. So the factors are x plus 3, x minus 2, and x plus 5. Along the top of this table, I'm going to list the intervals that I'm going to test out where these zeros are what is breaking up the intervals. So if I think about going back to this graph here, the first either positive or negative interval, depending on the end behavior, would be from -infinity to the first 0, which is -5. So I'm going to write that in here. So x is an element from -infinity to -5. Okay. The next interval we're going to use is from -5 to the next 0 from left to right, which would be -3. So x is an element from -5 to -3. Then the next interval is from -3 to the next 0, which is from -3 to +2. And then there's no more zeros to list, so the last interval would be from from +2 to infinity. And if we're able to somehow test each of these intervals to determine if the function f of x is positive or negative in each of those intervals, then we'll know when the function is either positive or greater than 0 or negative, less than 0, and we'll be able to use those values to solve the inequality. So at the bottom here, I'm going to list what is the final result for f of x. So once we determine whether each of these factors is positive or negative, we can use that to determine whether f of x is positive or negative. Okay. So the way I'm going to use this table is as follows. I choose my first interval. So the first interval is x is an element from -infinity to -5. And I'm going to choose some test value in that interval. So it can be any value at all that is within that interval. So let's say we pick the value -10. Right? -10 is for sure in that interval. If I choose that -10 value and substitute it into each of these factors, do I get a positive or a negative result? So the first one, I would have -10 plus 3. That gives me a negative result. It doesn't really matter what the number is, just whether it's positive or negative. The second factor, I have -10 minus 2. That's definitely a negative value. And the third factor, I have -10 plus 5, and that's also a negative value. So if all three of these factors in the function f of x are negative values, when they're multiplied together, right, x plus 3 times x minus 2 times x plus 5, when those three factors are multiplied together, I get a negative result overall for the function f of x. So that tells me that in this interval, the function is going to be negative, because these negative values would be true for any test value that I pick from negative infinity to negative 5. Then we go on to our next interval. And again, we pick a test value for x that's in that interval. So here, my interval goes from negative 5 to negative 3. So let's pick the test value of negative 4. So if I plug in the value negative 4 to each of these factors, here, negative 4 plus 3, that gives a negative result. Next factor, negative 4 minus 2, that's definitely negative. And the third factor, negative 4 plus 5, gives a positive result. So now if I multiply these three factors together, a negative times a positive gives a positive result. So I know that the function f of x is positive in that interval. Going on to the third interval, an easy test value to pick would be the value 0 here, since that's included in this interval. So 0 plus 3, that gives a positive result. 0 minus 2 gives a negative result. And 0 plus 5 gives a positive result. So when we multiply the three factors together, a positive times a positive number gives a negative result overall. And finally, the interval from 2 to infinity, the value 3 is in that interval. So if we plug in 3 to each of these factors, 3 plus 3 is positive. 3 minus 2 is a positive number. 3 plus 5 is a positive number, and multiplying three positive numbers together, we get a positive result. So now I know that the function f of x is negative in two intervals and positive in two intervals. And I want to go back to the original inequality. I want to know, when is f of x less than or equal to 0? Well, I know it's equal to 0 at x equals negative 5, because that's one of the zeros. I also know it's equal to 0 at x equals negative 3, because that's another 0. And I know it's equal to 0 at x equals positive 2. And I know the function is less than 0 in this interval, because the function we figured out was negative there, and in this interval. So those are all the x values that I want to include in my solution set. So again, we can write out our solution set is x is an element from negative infinity to negative 5. We want to include that interval. I want to include the negative 5 on that endpoint. And also from negative 3 to positive 2. And we want to include the negative 3 and include the positive 2, because those are values where the function is equal to 0. If our inequality was a strictly less than symbol and not equal to, then our solution set would include open brackets where the zeros are instead of the closed brackets there.